Our objective for this heat transfer project was to understand thermal radiation. We did this by constructing two solar ovens of different configurations, one that was air-filled and the other one that was evacuated. And then we compared our experimental values and our calculated values. There are many types of solar ovens out there, some that use reflectors, some that use mirrors. We found one that actually uses an evacuated tube, and we were intrigued and we thought we would try and design and build one of our own. The GoSun stove, it's a solar oven that uses an evacuated tube, which is like a vacuum between one tube inside of another. And what this does is it effectively insulates the inside oven, allowing radiation only to penetrate it. So since solar radiation doesn't need a medium to travel through, it effectively penetrates this vacuum layer and it gets really hot inside because that solar heat is trapped inside. This allows it to get really hot, advertised up to 550 degrees Fahrenheit, cooks in 20 minutes, cooks in the cold, and we wanted to see, well, what can we build one of these ourselves? As is common knowledge, solar ovens are designed to work with the sun, and so if you have rain or overcast conditions, they don't work quite as well. The conditions that we actually performed our experiment were cloudy and slightly rainy, and so we'll explain a little bit about the type of results that we got from the experiment that we did. So we attempted to recreate our own solar oven by using a FoodSaver vacuum sealing system to effectively evacuate the air in between two mason jars. We call this the annulus, which is that region of space between the two mason jars. We filled each of these black mason jars with about 100 grams of water, and then for the air annulus, simply placed it inside. For the evacuated annulus, we used the vacuum sealer to remove that air. We thought it wise to perform two tests at the same time to assure our data. And so you see 4 solar ovens out there. There's still the 2 configurations, the air and the vacuum, 2 of each. So we let these collect out in the sun for about 2 hours to collect as much radiation as necessary for a temperature change. We built some makeshift parabolic reflectors to help improve the solar radiation collection. We found that they didn't make a big difference, although they did look very nice. After about 2 hours of this solar collection, we brought in our ovens and opened them up and measured the temperature change. Starting at 10 degrees Celsius, the air-filled annulus got up to 19 degrees in that 2 hours, and the evacuated annulus got up to 23 degrees. So there wasn't a very big difference between the air-filled and evacuated for our given circumstances, but we imagine under much more intense solar radiation, we would have seen a lot more dramatic difference. The way that we were able to proceed with our calculations and understanding what was happening with radiation was we used a solar meter to measure the incoming radiation that would be incident on our solar ovens. And as we've done for calculations in class before, we used the effective cross-sectional area from the top view of the solar oven to estimate what the effective area of heat transfer was. A couple assumptions that we made for this project is that inside the evacuated annulus there would be minimal convection. Also that the outer jar would reach equilibrium with the environment, so 10 degrees Celsius, and also that the emissivity of glass would be 0.92, which we found from a table. On average, we measured about 200 watts per square meter of heat flux. To calculate this, we used the resistance method as recently discussed in class, and found that by dividing the radiation by its effective solar incident area, we got 223.88. Now this is about 12% error from what we actually measure with a solar meter, which is not bad for backyard science. Using the energy equation combined with the resistance method that we discussed in class, we're able to solve for H for the two different conditions. One, using the 200 watts per square meter that we measured using the solar meter, and two, the calculated value of 223 watts per square meter calculated previously. Putting in numbers, we get that H equals 15.3 and 17.2, which comes to still about 12% error. To sum it up, from this experiment, we are quite happy with the data that we were able to collect, especially in comparing it against our calculations. For our heat transfer coefficient for the annulus filled with air, we got an H value of 15, which, referring to a table, is within range. 2 to 25 is the range. So we were quite happy with that. Also for our radiation, we measured 200 on average with our solar meter and calculated 223, which was at 12% error, which we were quite happy with as well. Now the effects of a cloudy day on a solar oven were quite apparent. On average, we see between 900 and 1100 watts per square meter versus the 200 that we measured if you were to consider a sunny day and not a cloudy day. We also were experiencing some rain. And so that is effectively why solar ovens don't work that well, because the solar radiation is scattered and absorbed in the moisture and in the clouds. So overall, we're quite happy with our results. We do appreciate any feedback you guys give, especially any changes that we could make if we were to redo this experiment for a sunny day.